A process is a sequence of events that unfold over time. And that is not specific to computing, to computer science. A process is a set of activities that interact to produce a result. The activities unfold according to patterns that describe or prescribe a process. Okay. That comes from Wikipedia, must be right. Okay, so that's a very general definition of what is a process. But I said that processes are not specific to computing. They are everywhere. They permeate our nature and culture. They are our way to understand what happens. So anything that happens in time, and it happens as part of what we can call a process. For example, in physics, galaxies and solar systems form over time. They follow a formation process. So physicists describe the processes, how these large-scale entities form over time. In the small, in biology, you have metabolic pathways in our bodies that unfold over time. So what chemicals react with what chemicals? Well, that is a biological process. Political parties, legislature in government, courts, companies, they all follow processes. If you want to get married, you need to follow a process. You need to submit papers. You need to show up in a particular place at a particular time with a particular person. So all of that is part of the process of getting married. Industrial production is governed by processes. So what I'm saying here is that these processes are everywhere, and we can either describe or prescribe them. What is the difference? So anyone knows the difference between prescribing and describing things? Let's say a galaxy, a process the formation process of galaxies. Do we prescribe them or describe them? Anyone?
Yes. Describe them?
Yes, we describe them. There's no way to tell a galaxy how it should form. They are completely beyond our control. And that means the only way we can handle those processes is to describe them. But some processes we can prescribe. We can decide how the process unfolds. For example, if you are a lawmaker in a country, you can decide how, for example, companies should be governed. So you are prescribing the legal code for companies, for example, as a lawmaker. And that applies to our computation as well. And that's the power of computer science, is that we are able to precisely prescribe the processes that unfold in our computers. And computational processes are sets of activities in a computer that are designed to achieve a desired result. So our task is then to understand how these processes unfold and how the description or prescription of the process, our program, gives rise to the process. That is what we want to understand. We need to communicate these processes between the people involved. So programming is then a technique that allows us precisely to communicate computational processes between the architects, designers, programmers, the operators of the software, the users of the software. So programs prescribe the computational processes at the heart of these systems, and they can play a central role in the human communication during the construction and operation So don't think of programming as something that you do in order to make something happen in a computer. That will happen. Fortunately, or hopefully, your programs will be able to run on a computer. But what is almost more important is that your program communicates a computational process well to other people, because these other people will need to deal with your program. They will need to further improve it. They will need to find errors, and so on. So in a nutshell, if there's one sentence that you will take away from this module, it is this. Our motto in CS101S. What is programming? Programming is communicating computational processes. That is what we're interested in. That's what we are here for. We want to understand how we can effectively communicate a computational process primarily between people. Any powerful language, be it a programming language or be it any other language, provides the following elements. They provide primitives, words or individual sounds, for example. Those are the primitive elements of your language. And they provide ways to combine those. You can form sentences out of words, for example. And finally, a means of abstraction. That is, these are the three elements of programming. And and the means of abstraction, we will spend a bit more time with in a few minutes. Let's look at the primitives first. Primitive expressions. Now, in programming, we start with very simple entities. For example, numbers. You can write numbers in your programs. So that means numbers are primitives in our programming language. So for example, 0 is a primitive, and you can try to run this primitive as the simplest possible program. You press run here, and you see the system responds to you by saying, "Oh, there's actually an error in your program. You see there's a missing semicolon at the end of a statement." That teaches you that such primitives, such as 0, are not programs. Expressions, such as 0, are not programs. Programs we call statements. You can turn an expression into a statement using a semicolon. So that is probably the most simple program you can ever write. 0 semicolon is a program. You can run this program, and you see the result of evaluating the program showing up in the Source Academy. So you can write bigger numbers here, and the same thing. You turn the expression 420 into a statement using a semicolon, and you run it, and you see the result. You can actually form more complex expressions from these primitive expressions, from these numbers. And that's already a means of combination. You can combine two numbers using an operator. For example, you can write 1 + 2, and you press run, and that means you can use your Source Academy as a calculator. It computes the result of adding 1 and 2 for you. So we combine the primitives into larger expressions, and those larger expressions we also turn into statements using semicolon. Expressions are not programs. You've seen that I had to put the semicolon after the expression in order to turn it into a program. And the result is called then an expression statement. So 486 semicolon is a program. We have seen operator combinations, right? So a means of combination in these languages are operators. We can put an operator symbol between two expressions and form a larger expression, just like what you know in school already. That's the notation, and the notation follows the usual rules that you've learned in primary school. Remember, primary school, you learned that if you put parentheses around an expression, you need to do that first, and then what would we do next? 4 plus 2 we have to do first, if you remember your primary school, but then you have the minus and the times, right? What do we do next? The rules that you learned in primary school tell you that you do the multiplication. So if you have 4 plus 2, that is 6, you need to multiply with 3 before you subtract that from 25. If you want to give a name to a value, you can do that using a constant declaration. So that's another kind of statement. You've seen we have expression statements, but we can also have constant declaration statements. And for that, we use the keyword const. Const size equals 2, semicolon, and then you can evaluate this and thereby declare the name size to refer to the number 2. So then you can interact with this program. Once you have declared names, you can use those names on the right-hand side here. So you can do size here, and you evaluate, and you see the value of the name size is now 2. And you can do that in your program also. So after declaring the name size to refer to 2, you can say size times 4. You evaluate that program and you see 8 as the result. So the naming abstraction allows you to associate a name with a value. And what you can write on the right-hand side of this equal sign is any expression. So you can write more complicated expressions here. So 2 times 5 as the expression that will be used as the value for this name. And that means you have 10 times 4 should be the number 40 as the result of evaluating this program. So that's an abstraction technique. Why am I saying this is an abstraction technique? Well, we are doing this all the time. We're giving names to things, and that's allows us to think. So all of us have names, and that allows people to refer to us. And the same for anything else that happens in our mind. We give names to them in order to communicate. And that's the same as what we do in our programs. We give names to things to properly communicate them to other programmers. The interpreter of JavaScript internally keeps track of an environment, a table that lets us associate names with values. So that's sort of what goes on internally, so that it remembers next time you use that name, it retrieves the value from the environment. So we've seen that constant declarations allow us to add name value entries to this table. And what you need to understand is that there are pre-declared names. So for example, the name math_pi is pre-declared. So you can assume that it's there already for you. You run this program and you see its value. And you can use this math_pi anywhere in your program, and the correct value will be used. So those are pre-declared names that we have in our system. There's also functions pre-declared. So for example, we have a function pre-declared called math square root. If you write math square root, you are able to access this function that is already built into our system. You can think of our operators also as pre-declared functions. It's just that we use this particular infix notation to make use of those functions. They can be applied, the functions can be applied like you know in mathematics. You put the name of the function. In mathematics, you use probably very short names called f, for example. In computing, we use longer names for our functions, like math underscore square root is the name of the square root function, but we put the arguments like in mathematics between parentheses after the name of the function that we're applying. So this syntax, math square root, open parentheses, 15, close parentheses, applies the pre-declared square root function to the number 15. But that may be quite limiting. You may want to define your own functions. So you may want to declare functions yourselves and not just use the pre-declared ones. And that is the last abstraction technique that I'm covering today in today's class. That's called functional abstraction. We write a function declaration. And then we can make use of this function just like we have made use of the pre-declared function, math square root. So what does this function declaration consist of? It starts with a keyword function. Then comes the name of the function that we're declaring. Now, this is similar to the constant declaration that you've seen. The constant declaration declared the name size, and here we declare the name square. And in both cases, we declare it so that we can later in the program refer to those things. Then come the parameters. So we declare what arguments this function can take as a list of parameters. And then comes the body of the function. That is included in curly braces. And for now, in the first couple of weeks of the course, all our function bodies start with the keyword return. And the result of this function should be x times x. That means when we apply the function, the value that we get is the result of multiplying the argument that we're passing to the function with itself. So here's what is happening. We are declaring a function, like a constant declaration. A function declaration declares a name. Here we give the name square to the function. So the value associated with this name is a function. Well, that's interesting. So our names can now refer to not just to numbers, but they can refer to more interesting mathematical entities called functions. Good. So that's function declaration. And then we can apply the function. Just like we applied math square root, we can write a square, open parentheses, 14, close parentheses. When you look at such a function application, it doesn't matter anymore where the function comes from. It could be a built-in function, or it could be a defined function, a function that you declared yourself. The syntax of applying those two kinds of functions is the same. There are two things happening here. The first thing is that we're defining a function. We're saying that there is a function that takes a parameter x and returns x times x. That's one step to define a function. And the second step that happens at the same time here is that we give a name to that function. You can write function applications wherever you can write an expression. So you can put them inside of other expressions, just like you can put the operator combinations inside of other expressions. So they can freely combine those in the way you like it. There's a different kind of primitive value in this language. And that kind of value is called a Boolean value. And there are only two values in this kind. And those are called true and false. So you can write true and false in your program, just like you can write the numbers, right? So let me show you that. If you write the value true, followed by a semicolon, you evaluate it, So this primitive expression true has the value true. So that's a new kind of value that we now have in this language. Then we can form predicates. We can take decisions based on these Boolean values. And one such a predicate you see at the bottom here. X larger equal 1 is a predicate. You take a number X and you compare that number with the number 1, and what you get back is a Boolean value. You get back either true or false. And then you can take a decision based on that value. So let's take a closer look. So here's a function that takes X as a parameter, and it returns the result of applying this comparison operator, greater equal to X and the number 18. So this is a predicate. For example, you can apply the function adult to my age. I'm 29. So you press run and you see, I am an adult. My age 29 qualifies me for this predicate adult. So you see here all what you have learned in today's lecture in one program. You see primitive values such as 29. You see naming abstraction. We give a name to a function. That means we use the naming abstraction. We use functional abstraction. We declare a function that returns a Boolean value that is the result of applying the larger equal operator to the argument X that we're passing to the function. And the result is a Boolean value that you see here on the right-hand side. And then we can make use of these. That's the last idea in today's lecture, is we can make use of these predicates in what we call conditional expressions. These are particular kinds of expressions that allow us to evaluate one value or another based on the result of evaluating the predicate. So if you have here adult my age, if that result evaluates to true, the result of evaluating the entire expression is the result of evaluating the first expression, the one after the question mark. So this conditional expression lets you evaluate one thing or another based on the result of evaluating a predicate.